Welcome, everybody. My name is Zoltán Nagy, and I would like to welcome the audience in this mini conference. So first of all, I would like to tell some words about why application-specific integrated circuits are important today. So the well-known fact that the rapid improvement of information technology in the last 40 or 50 years is thanks to the Moore's law, which state that by improving manufacturing technology, the number of transistors that can be integrated into a single chip can be doubled every 2 years. But this effect is slowing down. On the other hand, another observation was done by Dennard, which tells that the operating frequency will double every 2 years. But as you can see on the right side of this figure, while the number of transistors are growing in the last years, the operating frequency denoted by green dots in the figure is flattened out, and it cannot be improved because the power consumption, power dissipation of the chips are very high. So integrated circuit designers have to search for alternative design options to provide the ever-increasing performance requirements of the users. So in this case, because frequency improvement is not possible, so we cannot create the same or similar designed processor in a new technology and gain performance. We should search for other ways, and this means that somehow the designers should utilize the more and more transistors which can be integrated into a single chip. So in the first step was that designers integrated multiple execution units into CPUs. So this was in the early 80s. The superscalar and pipeline CPUs appeared in professional and in home computers too, which provided increasing performance. But it soon turned out that the depth of the pipeline to improve the clock frequency of the CPU cannot be deepened, and also widening the execution path is not a viable option. So the multi-threading processors appeared, which contains several CPU cores. In the current server processors, the number of CPU cores are over 64 today. On the other hand, using a different design philosophy, much simpler processors on GPUs can also use for common tasks, general purpose task, which contains in today 5 to 10,000 cores. But even if these processors provide high performance in paper, it is in some cases very hard to achieve this performance. So efficient programming of these architectures are hard because special knowledge is required to create parallel hardware. And in some examples or in some problems, simply the number of simultaneously executable instructions is small and cannot utilize a pipeline or 5,000 cores. On the other hand, if we examine the silicon die of current microprocessor, we can find that the floating point unit and the arithmetic unit, which do the real computation, takes only 10 to 20% of the total surface. So as you see on the right side, the areas marked by red are the floating point and the arithmetic logic unit. And in the 4-core processor with level 3 cache, it is only a small fraction of the silicon die. So all the other parts, caches, branch prediction, decoding units, and so on, are required to execute the instruction and move the data close to the execution. So designers started to create special functional units And usually they target functions which are used generally in the majority of users because otherwise they waste silicon area. So the first example was the graphics processors, for example, for 2D functions, which was able to draw simple shapes, bitmap movement, and very simple operations. These are the graphics card in the end of 80s and beginning of the 90s. After the gaming industry is evolved on the conventional PCs, 3D functions are implemented in graphics processor, for example, triangle projection, filling and shading, texture mapping, and triangle visibility computations are done in a special chip, and each step gets its specialized unit. Because these chips was commonly used by a large user base. They were efficient to manufacture and profitable. Another example is image signal processors, which is included, for example, in mobile phones to handle the mobile camera of the phone. These do processing, filtering, and simple image processing task. Another example is network processors, where the IP and TCP traffic coming from a network is offloaded from the microprocessor, and the specialized architecture process the packets and places it in the appropriate position in the memory. Similarly, in high-performance system, remote DMA is used where the network card can directly copy data to a remote node memory. Another example is video encoders and decoders. So as, for example, we're streaming this video or this presentation in Zoom, the video frames are encoded by a special unit in my laptop. And this is also a common use of a special functional unit. And the latest trend is use some AI or deep learning neural network accelerators into the processors and improve the performance in this area. So designing application-specific circuits has a very long design time, especially verification, because we need to be sure that the circuit we created is working at the first try, because current manufacturing technologies below 10 nanometer are quite expensive. So just creating the MOSFET and designing a processor takes at least $100 million or more. If some mistake is done, then the whole process should be started and another $100 million should be spent. On the other hand, when going to a new manufacturing technology, it provides less and less benefit just now. So as in the past, we can expect that the clock frequency doubled and the number of transistors also doubled in a 2-year period. Today, this is a smaller factor, and in many cases, only some 10% or 50% improvement can be done. However, in old mature technologies, which is also appropriate for less demanding applications, speaking 28 or even 90 nanometer, they are more cost efficient. So in this case, small firms and small projects are able to create its own chip. So for example, in the so-called shared die project, where several circuits are implemented in the same die, can be started at $10,000. But the manufacturing time and the design expertise is also required to design this chip. So another alternative solution can be the programmable logic devices, for example, field programmable gate arrays, which you can see on the right side of the image. So in this case, we have so-called configurable logic blocks, which contains lookup tables, which can do arbitrary logic functions, registers, some logic circuits, adders, and other blocks are available. And it is connected by a programmable interconnect network. And we can tell it that this is some kind of reduced breadboard, which can be programmed by the user. And if we created the bitstream for the FPGA, then the new design can be tested in a couple of minutes. And if we find some error, it is relatively easy to correct it and load another bit stream, and we can continue working. So you don't need to wait long respins. So according to this paradigm, we have a programmable hardware, so we can create an architecture which is specific to the given algorithm. So not the algorithm is optimized for the given processor architecture, but we create a dedicated architecture for the given processor. This means that our execution unit can work in parallel and can be connected directly on the silicon die, and only the required circuit elements are implemented. So all the not necessary elements, for example, if we don't use floating point unit computations in an algorithm, just integer, then we don't need floating point. So we convert the hardware to the algorithm. As a result, in some applications, we can achieve 2 to 3 orders magnitude increase over the CPU core, while the power consumption of these devices is relatively low in the 1 to 40 watt range. So today, this morning, I would like to show you some presentations where we show what kind of applications we do on programmable hardware. So, and our next speaker will be Peter Szolgay. Peter, the floor is yours.
Good morning. The title of my talk is From Cellular Neural Networks to Many-Core Digital Architectures. Let me give a brief, very brief overview about what is the cellular neural networks. Cellular neural networks or nonlinear networks are analog processor array working on a regular and arranged on a regular grid, and the interconnections are locally. It is an important from implementation point of view. It is a very important feature, and these local interactions are mainly, not always, but mainly if we want to implement it a physical system, then it is not true. But if we want to solve an image processing problem, then these interconnections are space invariant. That means everywhere in the array, the processing elements are interconnected with the same weights, and these weights are the real program of this architecture. But to build up an analog processor array, this is the CNN universal machine, which was invented by Professor Oshka and Professor Chua in Berkeley. It is all not only the CNN cells are on the chip, but some local memories and global memories controlling the whole operation of this architecture. And they could prove that this is a universal machine. That means in Turing sense, what a Turing machine can do, this architecture can do also. But they don't say anything about the efficiency. Maybe in some cases it is not very efficient, some cases, but it is in generally, it is as general as a Turing machine. The Turing machine, in other words, it is a hardware, what we want to do. And based on this idea, there was a competition between the different laboratories mainly in Europe to build up such chips and such an architectures. And finally, the red small camera, like a matchbox size, camera is an industrial product of the Hitachi at the moment. That means the theory went to the practice and applications. Why was this competition? Because this computational architecture exhibits a lot of computational power. Namely, these tiny chips could work in some cases to tera operation per second, which is huge. Incredible, huge, low dissipation. And coming back, the only thing what was a shortage of this architecture, the accuracy. In analog VLSI technology, the 6-8-bit accuracy is the maximum which could be achieved. And therefore, it was an interesting question, and Professor Nagy and other colleagues introduced emulated digital implementation of this computing unit. Namely, we have a memory, a template memory. The template memory, the weight values, or that means the programs, and the arithmetic unit, which the arithmetic unit do a computation which is derived from the original CNN equations using discretization in time. The discretization in space, it is provided by originally the processes were discrete. And the goal of several things here we could program in this architecture, and it was implemented as on the last slide you could see an FPGA, and also almost the same architecture was implemented in a CMOS called Castle architecture. The Falcon is architecture is very similar to this one, and it was implemented on an FPGA. But what we want to solve we want to solve the problem that there is a universal machine flow or an algorithm, let's say so. Data flow of running on a 2D or 3D array, and we try to optimize on respect to area accuracy. Area is very important because we pay at the manufacturing for in square millimeters. And if it is large, then we have to pay a lot. Then it is not so advantageous. The accuracy is also the speed, of course, why we use an array and why we use something which is not so comfortable, not so common, because we want to have a faster and better solution. The better means in some cases that dissipated power is lower and the bandwidth is critical, the IO number of the IO connections. And a couple of months ago, I could see that it is could be critical also. And optimization criteria is the reliability of the system. If you want to consider a self-driving car, then it is absolutely crucial the security. That means the reliable operation of the system. And of course, there are some limitations. The physical processes which can be implemented on a given area, the number of the size of the memory on the chip and the off-chip memory. And it is an important question how they can communicate and interchange the data. Even if I have a very, very efficient computing arithmetic unit, very strong, but I cannot remove the data, or I cannot feed with data the processors, it is not a good solution. And as the first, I would like to show you some examples without any details. I'm sorry that but I want to show you that because it is these were interesting tasks, and different optimization criteria was in the focus of different examples. The one is the computational fluid or air dynamics, which is suppose that this is an investing adiabatic compressible flow, and that there is an obstacle, there is a step in the area. Perhaps Zoltán is going to show some more details than I. You can see this mesh structure is an unstructured mesh. That means that the mesh sizes are different. Where the most important changes are, it is more dense. If there is nothing happened technically, then the meshes could be quite large. And of course, in this case, the speed is critical, the area is also critical, but the communication between the outside memory and the inside memory is also, and therefore, if we do nothing, this bandwidth is very high, and these blue areas means that the communication facilities or requirements, and if I restructure, renumber these tiny places and arrange so the memory, that means that the bandwidth will be drastically decreased, and this is a good thing, and this is the final flow of the what we could see, and the speed and the density map you can see here. Another problem is the retina model. Retina model is a crucial thing, was a crucial thing at that time when many years ago we have made it, and this problem was specified by the biologist, and this the model was quite complex. The ordinary set of ordinary differential equations was given the cell body, and the axons were also dynamically excited or inhibited, and this model was running on a traditional PC 1.5 days. If a simple step function was not a very complex one, but on a simple PC roughly 10 years ago, it was more than 15 years ago, it was running on 1.5 days. And therefore, the motivation was whether this emulated digital Falcon architecture can improve the solution and accelerate the operation. And the arithmetic unit has different parts, but I don't want to go into the details. But one thing I want to focus that what is the accuracy which is required, the computational accuracy. And we don't know. Telling the truth, neither the biologists, it is a bad question for biologists. It is not a good question for at the beginning for us. We suppose that if we use a floating point solution, this is an accurate solution. And changing at the fixed point, different fixed point operations, we could see that the 20-bit operation, instead of a floating point, a fixed point 20-bit, it seems to be good enough. Professor Verblin at Berkeley told once that if our brain should process in floating point, we would be totally blind. We could see nothing because the capacity in our brain is not good enough. Another example is the neural measurement, which will be presented by Zoltán Kincses and his colleagues. How to measure and classify on the spot the spiking neurons. The spiking neurons deliver the information used in the spike train, and we have to somehow select and classify somehow in real time as they are coming. And it is an interesting question. The next example is the sense and the void. In this picture on my left, you can see some further development of this project. And the problem was that there is a blue unmanned air vehicle there, and there is a red dot normal airliner, and they should not collide. What they should do on the blue airplane to avoid the collision, and it was built and built the idea behind this implementation is a Kalman filter to identify and predict the trajectory of the red airplane, and using knowing this information, we try to avoid the collision. And every computation should be done on board on the blue airplane, and but the engine of the airplane is supported by an accumulator on the board. But all the computation requirements have to be supported by energy also on the board, and therefore it is not only the area, but the dissipated power is a very, very critical issue in this case. Next one is we are trying to move, and we are searching, and we could identify that there is certainly a limit of the CMOS technology. And everywhere in the world, in the research laboratories, they want to find some solution. What would be the next technology? And one candidate is the micro nanomagnets. And to compute the potential field of this structure is a method of using the fast multipole method, which is critical, not only in this application, but other applications. And my last example is if we want to or try to control a single camera and head-mounted camera, operation of a slightly handicapped person in a kitchen. Typical actions, they have to recognize the cans, the pans, the glasses, and so on and so on, and they have to catch it. Perhaps it is not he himself, but a robot arm may help him. And in this case, there are two important places where we try to help and accelerate the process, namely to identify in a kitchen. There are different objects and select the glass what I want to catch. It is the object selection, and there is after selecting the object, we have to find the boundary of the selected object, the bounding box. And using this bounding box, we can accelerate the identification of the object. Why it is important, but if it is a glass, if the robot arm has a very high force, too large force, I will broken the glass. If it is not large enough, it will slip out from the hand of the robot. Therefore, and I don't want to go into the details. I was running out of my time. Let me conclude my talk that there are some basic ideas which were coming from cellular neural network in many core architectures. And it is an important question when I have to step from, if I have a sensory array, for example, which are providing analog signals. This can be pre-selected and filtered using this analog array, and it is an important question. When I have to go to, finally, I have to go somewhere in digital world. Where I have to go to change from analog world to digital one. And to complex problems, dedicated inhomogeneous architectures could be designed and optimized using some technological step, and the problem specification can be done on high-level language. This is to map the high-level language to hardware, the Turing church thesis, which is the basic theorem of the theory of computation. This provides that it is feasible, it is possible. In every case, if you have a high-level language implementation, a software, then you can map your problem in hardware in a Turing machine. Thank you very much. That's all.
So my presentation will talk about an overview of methods for mitigating catastrophic forgetting in deep learning networks. To start off, I would just briefly talk about what we mean about a deep learning network. When we talk about this term, we usually think about an architecture like we can see on the left-hand side here, where we have an input layer, we provide the data regarding of what actually the data is. We can break it down into a set of numbers, which we can provide as input. We have some hidden layers in between the input and the output layer, where the output layer can be a classification or the prediction of an actual value and so on. The hidden layers can be many, and indeed in today's modern networks, we have dozens of layers inside the network, and they can be of different types. Here, what we can actually see are what we call a fully connected layer, but we can have convolutional layers, normalization layers, and so on. But this is usually what pops to mind when we think about deep learning networks. Now, a node, one of these blue dots that we see on the left-hand side, is expanded in the on the right-hand side. Every node has an input, a set of inputs, but every input has a weight attached to it, which basically modulates the importance that that input will have on the value calculated by the particular node. Inside the node, there's a calculation done using the input values and the weights attached to each input value. And also there's a value which we call a bias, which is particular to the node. So it's not something that has been received from outside the node, but it's particular to the node, and it's also a learnable parameter within the functioning of the network. Once this is the calculation is completed, the value, the obtained value, is passed on to what we call an activation function, which is basically the nonlinear part of the learning process here. Most of the successful activation functions used in today's deep learning networks are nonlinear and provide that, that possibility to learn complex tasks. And obviously, once the activation function is generating a value, that value is considered the output of the node, and the output will be an input to nodes on the next layer of the network. Just a moment on how memory is formed in the brain, because more or less our aim in constructing these deep learning networks is to mimic the brain, the human brain. If we can do that, then more or less our job is done. The human brain, as we can see, if we think not biologically, but a little bit technical about it, can be interpreted as an ensemble, a grouping of different networks, each with its own little role in constructing the whole process of reasoning, classification, if need be, and storing of information. Like if we are talking about explicit memories, these are things that happen to you or general knowledge, then a role in forming these memories is played by the hippocampus, the neocortex, and the amygdala, which are small parts of the brain, as we can see on the image. The implicit memories, which are more or less motor memories, fine skills like riding a bicycle and things like that. a role is played in forming these memories by the basal ganglia and the cerebellum. The prefrontal cortex, which we see with the color green on this image, is what we would call a short-term working memory. Basically, information about events, about what happens to us, is constructed, is stored for a short period in the prefrontal cortex, and then it is transferred into a long-term memory, usually within the sleep period, when the human brain is not continuously excited by our sensors, but by our senses, then it has the time to transfer significant relevant information to long-term memory storage. As I mean, not wanting to become extremely philosophical here about will we ever be able to create emotions in machines, but an interesting note is that the amygdala is attaching an emotional importance to memories. Sometimes memories formed in a fearful event, yeah, which are deeply rooted within us. If something really scared you, then you will probably remember it for the rest of your life. Are constructed with the help of some hormones from the amygdala. Now, the actual term of catastrophic forgetting, if I would have to give a very simple example of what catastrophic forgetting means within the deep learning networks, I would probably give the example of a simple classification procedure done on handwritten digits. For example, the Modified National Institutes of Standards and Technology dataset, short of the MNIST dataset, where there is a large number, about 60,000 handwritten digits from 0 to 9. In small 28 by 28 images, which the network can learn to classify. You show them the digits and it will correctly classify them as which digit they are. This data set is very used because it sort of provides a common benchmark for network performance. A relatively simple deep learning network with just a couple of hidden layers is able to achieve quite high accuracy results on this data set, being able to correctly classify about 95% of the validation data set of this MNIST data. Now, as I said here on this slide, the deep learning networks are one of the most successful machine learning techniques. I mean, with a simple architecture to be able to reach 95, if you add a little bit to the architecture, you are able to go even beyond 99%. So almost perfection, almost every validation test data is recognized and classified correctly with deep learning networks. Now, if you consider that from a mathematical point of view, there is a solution to this problem, meaning that weights and biases can be learned by a network like this to classify almost perfectly every test data, then you would assume that taking that particular network, showing it, I mean, training it only with the digits 0, for example, and maybe just one example from the other digits, the 1 to 9, so that the network knows that there are 10 classes available for classification. When you test, when you validate on the full validation data set of this network trained only on zeros, you obtain an accuracy value of 10%, which is expected. Now, it only recognizes one of the 10 digits, the zeros, the other ones, it doesn't know what they are. Then this trained network, if you continue to train it with all the ones, for example, yeah, so you take the next class available and you show all the samples to the network, on first blush, your instinct would say that now testing on the whole testing data set, like all 10 classes, would probably yield a 20% accuracy, because it knows the zeros and it knows the ones. It knows 2 out of 10 classes. But that's not the truth. It will still yield a 10% accuracy, because it will, in the second part of training, on the second step of training, it will optimize to recognize the digit 1 in the detriment of knowing what digit 0 was. And this is what we would call the stability versus plasticity dilemma. These weights and biases, which are the learnable parameters within the deep learning network, should they be stable because we've learned something, or should they be plastic? Should they be easily changeable because we are trying to learn something new? Well, the standard architecture, like one I've shown on the previous slide of a deep learning network, are basically built to learn the task at hand. They are very good at optimizing, finding a solution, a mathematical solution for the weights and biases that will satisfy the task at hand. They are not created to store different kinds of information. As you remember in the slide about the human brain, we were looking at it technically and noticing that they are different networks for different types of uses within the brain. These initial weights and biases are basically just a starting point for optimizing them for the task at hand. It doesn't matter if the initial values of weights and biases were some random initialization, which we actually do on the first step of training, where weights and biases have to have a value. So sometimes we randomly initialize them, sometimes we will set them to 0 and so on. But even if these values are actually learned values from an earlier stage, the network usually just disregards that fact and optimizes their current value for the second step of training, for the current task at hand. Now, I've tried to categorize, to put some mitigation methods into some different categories with some examples in this table. When we talk about regularization methods, they are the ones that add constraints to the network's weight updates. Like the updates of the weights and biases is not freely flowing during the backpropagation of error in the learning process, but there are some limits set in order to protect some of the weights so that forgetting doesn't occur. Examples are these dual weight architectures. Some early implementations had weights that were called fast and slow. Fast learning, meaning very plastic weights, weights that were easily changeable from learning new samples, new data. and other weights that were set as being slow, meaning they were very hard to change. They were very stable, even in the face of new information shown. Kirkpatrick et al. Had a very good proposal in 2017, which they called elastic weight consolidation, which we'll talk about it in a moment a little bit more in detail. Another category called ensemble methods is, as you can see from the categories of these methods, we are indeed trying to mimic the brain, but there are so many things happening in the brain that it's hard for us, at least at the moment, to implement all the solutions, the technical solutions, let's call them, that happen in the brain to implement them into a current deep learning network. The ensemble methods are the ones that put multiple networks together, and they train them and then combine them to create a final prediction. Some explicit ensemble methods, such as the Learn++ or the TradaBoost implementation, they try to prevent forgetting by training entirely new subnetworks for new tasks that are presented to the network. The lifelong machine learning, for example, is a little bit more complex, because it basically decides whether a new subnetwork should be added to the ensemble or not. Well, the implementation of simply adding new networks when new tasks are presented obviously has the disadvantage of memory usage, which will grow with every new task that the network is presented. And also the fact that parts of an existing already trained network cannot be reused, even if appropriate, for learning new tasks. Rehearsal methods. Well, if you remember the example that I gave, that a simple network can learn all the digits, all 10 digits, to recognize all digits when presented with all the data at the same time. Well, the rehearsal methods play a little bit on this card, in the sense that they retain and replay some samples from past sessions or tasks when learning new tasks. This is so that the network shouldn't just focus on learning the new task, but it should sort of remember what the old task was with the few samples that are replayed during the learning of the second task. Sometimes they're not actual samples that are replayed, they are just generated pseudo samples that basically extract the statistical essence of the previous task. Sometimes networks will actually add new neurons to some layers to satisfy newly acquired information. And yeah, that Gebhardt had a proposal where that is colloquially called JEPNet, that we will again discuss shortly in a moment. The dual memory methods are playing on the card in the brain, where I was saying that from the short-term memory in the prefrontal cortex, usually, not usually, all the time, memory is, information is transferred to long-term memory. So these methods employ two classifiers with different learning rates. One classifier that is very plastic, that is allowed to change very drastically and very quickly in face of new information, even if classification is not usually that high level. But then this information is transferred to another part of the network, to the second network. That's why dual memory methods, where weights and biases are much more stable and can change at a lower rate in order to protect already acquired information. And sparse coding methods, again, play on the observation that the human brain has billions of neurons, but to remember one specific task, there's a pathway that describes the memory in the human brain, but that involves a very low number of neurons compared to the total number of neurons available. So these methods are trying to reduce the chance of interference with previously learned tasks by selecting just the minimum amount of neurons necessary to be able to achieve a particular task. Right. For example, the Calm implementation that is given as an example on the right-hand side is searching among competing nodes of the network to see which ones have not been committed to another task, and those ones will be used for learning the new tasks. Right. So very briefly, because I am probably running out of time, about elastic weight consolidation, which is a good example of a regularization technique. If you can think of the learning for task A as a space within the solution, as a particular limited space within the solution space of the weights and biases. You can consider that theta A as the perfect spot which is achieved by the network as in the values of weights and biases for learning task A. Now, the low error area is represented by the gray ellipsis on this graph. For learning task B, if we consider the low error area as the yellow or cream ellipsis on this task, you can see that there's some overlap in between them. If you would allow the network to learn task B without any penalty, without any constraints, the particular spot, the collective result of weights and biases will be at the end of the blue arrow within the middle of the cream colored ellipsis, which, as you can see, completely outside of the low error area for task A, which will result in catastrophically forgetting task A. Kirkpatrick et al. In 2017 proposed this solution where there's basically a penalty function on the loss function that is backpropagated through the network, where some weights and biases that are important for task A are reduced in plasticity. They are allowed to change much less. So in order to drag the final result after learning task B, to drag it at the end of the red arrow, which is within the low error area for both tasks A and B. So at the end, you would not have forgotten task A. You would perform a little bit poorer than initially because you moved away from the optimal solution, but you're still within the low error area for task A, while at the same time being in the low error area for task B. And these penalty function, they act as little elastic bands, sort of, dragging the solution towards a desired space. So hence the name of elastic weight consolidation. PathNet is an ensemble, for example. This was a network that was trained on different Atari games. I mean, obviously, researchers use different methods to validate their work. For example, in boxes 1, 2, and 3 on the left-hand side of the graph, you can see the initial learning of task A, in this case, the game of Pong on Atari. And as you can see, from a very connected type of network, during training, box 4 in the middle column, top middle column, is the end of training for task A. Only some parts of this network are used to achieve learning a good result on task A. In box 5, in the middle of the graph, is represented the fixing, these parts that have been discovered as being essential for task A are frozen, are fixed, and then new parts are being constructed within the network to learn the next task, B. As you can see in the bottom half, the second task is learned much harder. You see the error rates of accuracy going much thicker, sort of up and down, because you have this limitation already in the network. And this is an ensemble because each module in this PathNet network is basically a network in itself. JEPNet is an interesting network that uses a self-organizing map as a hidden layer, where basically the inputs are organized topographically. I mean, on the right-hand side, you can see this, for example, for digit 5. As I said, the MNIST database is usually used by researchers because it provides a very good benchmark of your architecture, your network's performance. So if you want to learn the digit 5, there's topographically, that's the best sample that you have. The region around it is similar, yeah? And you can see that this map is self-organizing within learning, even if some parts of it on the top right-hand side are not performing as expected, where the self-organizing map is not able to cluster together samples of the same type. They have, the same researchers also proposed a version where they implemented a short-term memory buffer. And you can see that during training, yeah, after each period of training, they implemented what they called a sleep phase, where all the samples that were shown to the network before and stored only in the short-term memory buffer are replayed to the network, so they can affect the rest of the network outside the short-term memory buffer, where the weights and biases are much more static and are learning at a lower rate. And sparse coding, as I mentioned, sparse coding is based on the idea, this fixed expansion layer that is introduced after a hidden layer is basically, as you can see in the right-hand side of the graph, achieving the separation of useful versus not necessarily useless, but less useful neurons in learning a task, which after that will allow learning of new tasks with the free or available neurons in that are left. There was a paper that compared these methods, for example, and as you can see, as opposed to the baseline method where everything was shown to the network at once, every method decreases in accuracy, in performance. Yeah, you can see that for the MNIST database, accuracy is almost at 100%. And different methods have, these comparisons were done on the MNIST database on the CUB200, which is basically images of birds with 200 species of birds, so 200 classes to be classified, and the audio set, data set, which has been limited to 100 classes of audio signals taken from YouTube videos and labeled by humans. You can see that the different implementations have resulted in different results based on the type of work that had to be done. So as a conclusion, we are still far away, I would say, from implementing what the human brain can do extraordinarily efficient. Especially, it is said that the human brain uses about 20 watts of power and can do all these things that we have data centers that use megawatts of power and are not able to achieve at the moment. But this is our little slice of research, so hopefully we'll improve it over time. Well, thank you for your attention.
So I want to present you a short brief, let's say, about the sensor of autonomous vehicles and their placement. And just a second. Okay, what is an autonomous vehicle, or more exactly, or an automated vehicle? Refers to a vehicle equipped with technology that allow it to operate and navigate without direct human intervention. So these vehicles are designed to sense their environment, make decisions, and execute action to safely transport passenger or cargo from one location to another. In 2040, SAE, Society of Automotive Engineering, launched the SAE levels of driving automation. Let's say a classification of automated or autonomous vehicle. So we can see here in this image, we have 6 levels of automation. The first 3 levels are only for support, are features to support the driver, and the last 3 levels are automated driving features. Let's say here we can talk about the autonomous vehicle. Here is automated or automation driving. So we have different features that implemented in the vehicle that can be possible to classify the vehicle. So for the SAE level 0, we have automatic example of the features. We can meet automatic emergency braking, blind spot warning, lane departure warning. For level 1, lane centering or adaptive cruise control. So the system have control only for one of these, not for both. so have control or about the steering wheel or about the acceleration and braking. So level 2 have the both features included. Okay, as a first sensors used, let's say, in mostly autonomous vehicle or automated vehicles is video camera, and red, green, blue camera facilitates object identification, background separation, and scene comprehension by capturing comprehensive information, including contours of the entire sense. So here we have 6 cameras. The main cameras are here, are mounted here on the windshield, and the other 5, 6 cameras are mounted on the front bumper, on the left side and right side, on the side mirror, and on the back of the vehicle. And these are the most common location for mounting this sensor. In this configuration, it's possible 360-degree video monitoring of the vehicle, or mostly 360-degree. What is the biggest problem with these sensors? They can be affect the optimal function by the dirt or dust on the lens, and also of the sun glare. And another disadvantage is their capability to let's say identify objects in the night is a little bit lower. So these sensors are used mostly for traffic sign recognition, line recognition, and obstacle recognition. And okay, another sensor are radar. There are 3 types of radar: long range radar, short range, and mid range radar. Yeah, the area covered with blue and orange means the area, the measuring area of the sensors. So what is outside of these areas are blind spot. The integration of the radar technology can augment information obtained from other sensors. So by emitting high-frequency radio waves, radar captures data on the range, direction, and velocity of the object. They can function very well on weather condition, bad weather condition, and nighttime. However, it may have a limitation in defining small features. So nowadays, the radar is used in adaptive cruise control to measuring the distance to the preceding vehicles and adjusting speed accordingly. So the short range radar and mid-range radar are mostly used for monitoring blind spot from the mirror, and for system like parking assist, let's say. Okay. Here are some information about the measuring range of each type of radar. This is an average between 2 and 250 meters. And the short range radar measuring range has less than 70 meters. Okay, another sensor are ultrasound sensor known as, let's say, parking sensors. And they are mounted in the front and in the back of the vehicle, on the front bumper and back bumper, and can be utilized for short-range obstacle detection and avoidance. They are effective in detecting objects in close proximity to the vehicle, such as obstacle in parking scenario. They don't have a big measuring area and cannot be utilized for the features like adaptive cruise control or something like that. But its functionality is good on night, on bad weather condition. And another system or sensor is LiDAR, lighting detection and ranging. There are two types of LiDAR, 2D LiDARs and 3D LiDARs. The 2D LiDAR sensor provides information in a single plane, usually horizontal direction, and they offer measurement of distance and angle in a 2D space. So the orientation of the laser beams could be parallel to the ground or make an angle with the ground. Okay, when we have the situation when the beam of the laser are parallel with the ground, we have here a huge blind spot. The object, the animal, the obstacles which are here under the laser beam cannot be detected. That's it. That is an important problem. So we can use, let's say, two type of sensor, but it's not so cheap to use more sensor as LiDAR. So the 3D LiDAR sensor provide a more comprehensive view of the environment by scanning in multiple directions, including horizontally and vertically direction. So this enables a 360-degree field of view. The sensor is mounted usually on the central rooftop of the vehicle and can measure this area 360-degree around the vehicle and create such a mapping, let's say. Okay, but the form of the laser beams are the same in this picture, and also here we have some problem with the blind spot, because if the obstacle is too near by the vehicle, the LiDAR cannot detect them. So as I said before, 3D LiDAR is crucial for creating detailed 3D maps of the environment. This high-resolution mapping is valuable for understanding the terrain, identifying the objects, and planning the routes, because it works good in night on bad weather condition, but sometimes it has some problem with the glasses, let's say, with the building from glasses. Okay, the radar and radar are based on time of flight principle. Another important systems, or let's say sensors in autonomous vehicle, are inertial measurement unit is a critical component. It provides essential data about the vehicle acceleration, angular rate, and sometimes magnetic field information. Another important systems or sensors are GPS, Global Positioning System, which determines the absolute position of the vehicle on Earth by triangulating signal from satellites. Offers global coverage and accurate position information, and as a disadvantages can be affected by signal blockages. Example, tall tall buildings. So we so that all these sensors have some disadvantages due to weather condition, due to luminosity, due to their position or their capability to detect at a high distance. And in the vehicle are implemented some system like ADAS, Advanced Driver Assistance System. So what are these? What is this ADAS? Are system and technologies incorporated into vehicle to enhance safety and improve the driving experience. So this system rely on sensor fusion, what is very important, which involves integrating and combining information for multiple sensors to enhance the system's accuracy and overall the performance of the system. So here we have some features which are included in ADAS. We have features like adaptive cruise control, cyclist or pedestrian collision warning, forward collision warning, traffic sign recognition, blind spot mirroring, or park assist for traffic collision. So we talk about sensor, I talk about sensor fusion. So what do we need sensor fusion, or what is sensor fusion? It involves the intelligent integration of data from various sensors by ECU's onboard computers. These computers are enabled the real-time analysis of sensor inputs. So based on fast GPUs, or also based on different type of algorithms. Also, sensor fusion aims to create a holistic and accurate representation of the environment by combining the strengths of different sensors. For example, radar might be effective in detecting objects at a high distance, let's say, while camera provide detailed visual information. Another important advantage is, let's say, for the sensor fusion, these enhance system reliability by providing redundancy. So if one sensor type fails, let's say camera in a bad weather condition, or provide inaccurate data, the system can rely on other sensors for accurate information. So sensor fusion is crucial in ADAS because it allows the system to have more comprehensive understanding of the driving environment. So that's why we don't need only one sensor implemented on the vehicle. We need 2 or 3 sensors, even if there is a redundant information. Because to make a decision it needs more information. Decisions are based on the algorithm like fuzzy algorithm or something like Kalman filter, and what all the previous speakers presented today are very important for the autonomous and automated driving, because for autonomous and automated driving, we need also power electronics, fastest GPU, CPU, and also computational power. Also, we need artificial neural networks, cellular neural networks, and also for what we need all these. We need these in order to the system to be capable to sense the environment, to learn from the environment, to analyze the information from the sensor and to make a decision, and then acting in concordance with that decision. So here we have a Saturday Evening Post from 1950s. So what do you think? Is this really how the future will look like? So thank you for attention. If you have some questions.
So welcome back everybody. So after the break, we continue with the lectures. According to the schedule, the next speaker is Zoltán Kincses from University of Szeged via Zoom. So Zoltán, the floor is yours.
So thank you for your introduction. I would also like to welcome everyone in this workshop. I will present some details about our real-time spike sorting or FPGA-based real-time spike sorting system, but some historical background of our research. About 1 year ago, we started to cooperate with the neurobiologists at the University of Szeged. They are doing internationally outstanding research on the human brain. Their work has led to the development of a neural electrode that has been granted the necessary legal and ethical approvals to be used for measuring the neural signals of the human brain. The electrode developed by a neurobiologist team has been implanted in a patient diagnosed with epilepsy. As part of the treatment for epilepsy, the neurosurgical medical team implants a medical electrode in the patient's brain to determine where the seizures are began. This allows the neurosurgeon to determine where to start the intervene. At the same time, as the medical electrode is implanted, the neural electrode developed by the neurobiologist team is implanted with the patient's consent, of course. While the electrodes are in the human brain usually for a few days, the neurobiologists can collect data. The evaluation of the data is a very long process, and typically only after the electrodes have been removed from the patient can any results be obtained. Because it was very important for them to get some feedback during the measurements, they asked us to help them with a small, easy-to-use device that could quickly evaluate the results during the measurements. As the measurement process generates a large amount of data that needs to be processed in real time with a small portable device, we decided to use our multi-channel FPGA-based real-time spike sorting system. In my presentation today, I would like to present the details of this system and the most important theoretical background. First, let's start with the necessary neurobiological background. The brain is one of the most complex biological systems containing quadrillions of synapses and billions of neurons. To study this organ in humans or in animal models and to examine elementary neural mechanisms or high-order brain functions such as learning, sleeping, perception, and memory, three widely used methods can be applied. The extracellular measurement, where the electrode positioned in the extracellular space to record electrical signals from surrounding neurons. The intracellular measurement, where the electrode positioned inside the neuron, as you can see, here, and in the so-called intracellular space, and the clamp patch measurement, where the electrode positioned adjacent to the cell membrane, as can you see here. The extracellular electrodes can record action potential, so-called spikes, from the individual neurons, as can be seen here. These are some examples of some spikes generated by different type of neurons. The ability of extracellular recording to provide researchers with neuron level activity combined with its relatively low level of difficulty to perform has led extracellular recording to become one of the dominant experimental techniques in neuroscience research. For example, there has been a movement towards studying not only individual neurons, but networks of neurons in order to understand how the activity of interconnected neurons results in higher order functions such as perceptron, understanding movement, and memory. In traditional neuron recording system, which can be seen here, provide the direct interface to the brain, and the unamplified raw data coming from this point is sent outside to the body through wires to the rest of the data acquisition hardware. This hardware built up from a signal amplifier denoted by A, an analog digital conversion denoted by ADC, and a bandpass filtering with a cutoff frequency of 300 to 3 kilohertz. The raw data is recorded onto computer hard disk, and all data processing is performed in software. In the previous setup, the data is transferred from the subject to a computer via thick cables. These cables restrict the physical movement of subjects, thereby limiting the quality and diversity of experiments that can be performed. Furthermore, these cables can increase the severity of noise and motion artifacts seen in the recording during the processing phase. Cables are obviously invented in brain-machine interface applications as well, where the goal is for a patient to be able to lead normal lives, meaning they cannot be tethered to electronic equipment. These problems can be solved using a wireless recording system can be seen here, where only the result of the spike sorting sent to the PC. Let us begin by looking at the composition of the signals that are recorded by the extracellular electrodes. These signals are usually pre-low-pass filters in the analog domain and then sampled at a rate of 20 to 30 kilohertz. Different cellular mechanisms are responsible for different frequency components of the recorded signals. The high frequency content, about 300 to 6 kilohertz, is referred to as unit activity, while the low frequency signal content below about 600 hertz is referred to as local field potential. If unit activity is the signal of interest, then the sampled signal is bypass filter with a low cutoff frequency of 100 to 300 hertz and the high cutoff frequency of 3 kilohertz to 10 kilohertz, as indicated by its name. The source of this unit activity is action potentials or spikes from individual neurons. You can see here an example of an extracellular spike. The multi-unit activity is an action potential or spikes generated by many neurons surrounding to the extracellular electrode. The extracellular recording can be performed using, for example, a 128-channel high-density silicon-based probe, compressing closely packed electrodes arranged in 32 by 4 array with a center-to-center distance. So this distance is 20 micrometer. In order to obtain unit activity or multi-unit activity, the extracellular data is first bandpass filters, as I mentioned previously, to remove the local field potential and high frequency noise, and it contains only the spikes. We must perform spike sorting by sending this raw data through the signal processing chain to obtain single unit or multi-unit activity. The first steps are the spike detection, the process of separating spikes from background noise, and alignment the process of aligning all detected spikes to a common temporal point relative to the spike waveform. Once the spike have been identified, spike sorting can be take place. Most spike sorting methods are based on spike waveform information, since these methods are relying heavily on the assumption that each neuron produces a different distinct shape that remains constant to recording session. Thus, the first step in such method is some kind of feature extraction, in which spikes are transformed into a certain set of features, such as principal components that emphasize the differences between spikes from different neurons, as well as the differences between spikes and noise. After the extraction, another important step is the dimensionality reduction. Typically takes place in which feature coefficients that best separate spikes are identified and stored for subsequent processing, while the rest are discarded. Finally, spikes are classified into different groups corresponding to different neurons based on the extracted feature coefficient. This process referred to as clustering. The result is the sequence of spike times, also called a spike train for each neuron. This information can be represented graphically by a raster plot where ticks are drawn to indicate spike occurrences versus time, as you can see here. This data uniquely identifies each neuron. Some details of the first step, the detection. Nearly all detection methods involve two main steps: the pre-emphasis of the signal and the application of a threshold. Spike detection methods vary in how the signal is pre-emphasized and in how the threshold is determined. All of these methods run automatically given the detection threshold, so whether or not the algorithm is fully automatic depends on whether or not the threshold can be determined automatically. All of these methods are also real-time given the detection threshold, but automatic calculation of the threshold usually involves a training period. Spike detection was typically performed using a simple voltage threshold, which was set manually by the user. Some researchers have modified this method to include an absolute value operation before the compare equivalently compare to plus minus threshold. So for an automatic spike sorting system, the threshold must be calculated automatically. Automatic spike detection algorithms usually detect changes in the energy of the signal. One such algorithm is called the nonlinear energy operator, as you can see here, or the trigger energy operator. Automatic spike detection algorithms are based on some automatic or other automatic spike detection algorithms are based on template matching. If the spike waveform is interest are known a priori to the user, the meshed filters can be used to correlate the incoming signal with the spike templates. If the crosses a certain threshold, then a spike has been detected. A related method is detection using the discrete wavelet transformation, as can be seen in this last figure. The second step is the alignment. When spike detection is performed in the digital domain, whenever a voltage signal crosses a threshold, the window is amplified and a spike waveform is captured. At this point, each spike is essentially aligned to the point of the point of the threshold crossing. However, sampling jitter combined with noise effect may leave features of interest, such as maximum and minimum values, misaligned. The alignment process usually begins by upsampling the signal to help reduce the effects of sampling jitter. Then the signal is aligned to some event in time. For example, the point of local maximum or point of maximal slope, as you can see here. The third step should be the feature extraction. Feature extraction methods were also primitive in the early days of spike sorting. Often only were simple features such as the maximum spike amplitude, peak-to-peak amplitude, and spike width were used. This approach, although simple, is quite susceptible to noise as well as to intrinsic variation in spike shapes. A more sophisticated algorithm for feature extraction is principal component analysis. Besides for spike detection, the DVT has also been proposed for feature extraction. The DVT or discrete wavelet transformation should work well for feature extraction since it is a multi-resolution technique that provides good localization in both time and frequency. Methods have also been developed with the accuracy complexity trade-off in mind. One such method is called discrete derivatives, and is like a simplified version of a discrete wavelet transform. Another such method is an integral transform in which spikes are classified based on the areas under the positive and negative phases of the spike. Dimensionality reduction is a critical step in spike sorting for a number of reasons. The most obvious reason is that it will significantly reduce the required memory and computational complexity of clustering, resulting in significant reductions in the area and power of the spike sorting hardware. Another obvious benefit is that it reduces the output data rate of spike sorting hardware configured to output features only. The third reason that makes dimensionality reduction critical is that it improves the accuracy of clustering. A smart way to choose the features that can best separate clusters is by finding those features that have multimodal distribution across spikes, as multimodal distributions are an indication that more than one population is present in the dataset. In this slide, this approach can be seen. In this example, the distribution of amplitudes for samples 1, 2, and 3 are unimodal, so they would not be good choices of features to be used in clustering. Samples X and Y, on the other hand, have bimodal distributions, indicating that clustering of these features would reveal the two underlying populations with the data. The Lear force test, Hartigan's deep test, maximum difference test use this approach, for example. And the last step, and also maybe the most important step, is the clustering. Especially in our system, the unsupervised clustering is often the most difficult and most complex part of the sorting process. In the early days of spike sorting, the most common methods of clustering was manual cluster cutting. Extracted features were plotted on a scatter plot, and cluster boundaries were defined by hand. A more sophisticated method of clustering, which is now the benchmark clustering method, is in this field. Is called K-means. The K-means algorithm is based on the distance metric. The main benefit of using K-means is that it is a very simple and fast algorithm. However, a major drawback to this algorithm is that it is not unsupervised, as it requires the user to input K. One unsupervised clustering algorithm is called valley seeking. The idea in valley seeking is to first calculate the normalized density derivative and then to find the peaks of this function. The cluster boundaries are then identified as the regions between the peaks. Also another clustering method, for example, the supermagnetic clustering, or the OSOR clustering. The OSOR clustering is the only clustering algorithm which is both automatic and online, and that has a good accuracy complexity trade-off. And we use this clustering method in our work. So in our real-time spike sorting system, the NEO is used for spike detection because it is the most efficient among the commonly used spike detection methods, and it is easily implementable on FPGA devices. The NAO signal and the detection threshold is required. So here the NAO signal, and this is the detection threshold. In this algorithm is calculated, as can be seen here, where the xn is the end sample of the input signal, the cn is the correction factor, and n is the number of samples. The NAO algorithm works as follows. The raw input data signal fed into the NAO and the STD calculation block. The STD values is used later in our clustering process. When the NAO signal value is larger than the automatically calculated TN threshold, then the peak of the spike is detected. After a window around the detected peak on the actual channel is checked by the realign method. To ensure that the peak of the spike is certainly in the center of this window. As I previously mentioned, the correct alignment is crucial because the comparison cannot be done correctly with unaligned spikes, resulting in compromised classification. The NAO signal is a very high in amplitude when both the frequency and the power of the input signal is both high. In our system, the OSORT clustering algorithm is used, as I mentioned previously. The clustering and cluster merging threshold, TC and TM, are automatically determined and adaptively changed during the classification based on the STD value calculated in the spike detection part. The threshold value of one channel is calculated based on the standard deviation of a 5-second long moving window from the neural recording, where CC is the clustering correction factor, and NS is the number of sample points in spike. The OSORT algorithm works as follows. When the first spike is arrived, it is stored as the first cluster in the cluster memory. The next spike will be compared to the saved cluster mean using square differences as the distance metric. If the spike is similar to the already saved one, then the calculated distance is below TC, so it is assigned to this. If it is not similar and the distance is above TC, then the new cluster is created. This process is applied to the subsequent incoming spikes. After the assignment, the mean of this cluster will be updated because the composition of the cluster is changed. Furthermore, the cluster mean update changes distance between cluster means, therefore a distance check between clusters is needed. If a distance is below the merging threshold, then the updated and the closest cluster will be meshed together, forming a new larger cluster. I plan to briefly describe the field programmable gate arrays, but I will skip this part of my presentation because Zoltán gave us some introduction about the FPGA circuits in his first presentation. But one small thing. There is a special kind of Xilinx FPGA called Xilinx Zinc FPGA family, which was used to implement a real-time spike sorting system. The Xilinx Zinc FPGAs integrate a multi- or single-core ARM Cortex-based processing system called PS, as you can see here, and the traditional Xilinx programmable logic PL as in a single device. The PS also include on-chip memory, external memory interfaces, and a rich set of peripheral connectivity interfaces. Now let's see some details of our real-time spike sorting system. I will speed up my presentation because my time is almost over. So the spike sorting system can be split into three main blocks: the recording subsystem, the processing subsystem, which was implemented on the Xilinx Zinc FPGA, and the host PC subsystem. The neural data recorded with a 128 high channel high density silicon-based probe inserted into the brain tissue. Measurements of the brain signals with this probe were obtained with the Intel RHD 2000 electrophysical recording system at 200 kHz sampling frequency per channel with 16-bit resolution. These 128 channel recordings usually contain hundreds or thousands of spikes fired by dozens of neurons during a time period of 1 hour. The Intel RHD 2000 uses the SPI protocol to communicate with the Zinc FPGA. The schematic diagram of the processing subsystem can be seen on this slide. The system consists of an ARM processing system on the PS part of the Zinc FPGA and the memory controller core communicating with the off-chip DDR4 memory, the DMA controller core, and the spike sorting core implemented on the PL side of the FPGA. The spike sorting part is responsible for spike detection and the classification and consists of the multi-channel spike detect core and the multi-channel online sorting core. The role of RPS is to initialize the system with the pre-calculation of the required matrices and to start and control the sorting process and communicates with the host PC through an Ethernet port. The processing subsystem EER filter part, Butterworth EER third order zero phase preprocessing bandpass filter with 500 to 2000 Hz cutoff frequencies applied to the incoming signal from the Intel RHD 2000 recording system for noise reduction and to eliminate the low frequency content of the signal. The filter is implemented as two FIR filters combined together based on direct form 1 structure with 7 18-bit coefficient in each filter. The FPGA resource requirement of this preprocessing filter is very low, as you can see here, one block RAM and only one DSP slice. The multi-channel spike detect architecture can be split into the STD, the NAO, and the real-time computation parts. The STD computational part is responsible for computing the standard deviation value of the incoming signals using the 5-second window. The NAO computation part, the spike detection is performed by calculating the NAO signal and detection threshold, and the real-time part of the multi-channel spike detect is responsible for alignment of the detected spikes. The architecture of multi-channel sorting core is shown in this figure. The incoming detected spikes are serialized, and then the following 4 steps are performed: loading the spikes and compare it to the cluster means in the cluster memory, update the chosen cluster mean or create a new cluster, compare the cluster means to each, and finally merge the clusters. And the task of the host PC is only to visualize the results of the spike sorting and validate the sorting algorithm using hybrid ground truth neural data generation when the signal generator is operating. You can see here the resource requirement of our system, but I think I will show only the performance, which you can see here. Our FPGA-based system is 80 times faster than the PC-based MATLAB implementation, so it can be used real-time. And we also measure the accuracy of our system, and in many cases, for example, if we increase the number of neurons with high SNR, the accuracy is also acceptable. And finally, some pictures about our system. The results of the spike sorting using a cortical measurement obtained with the 128-channel silicon probe from the anesthetized rat can be seen. Contains some example clusters from two distinct channels. A and B is the different channels of the electrodes. On channel 2 or channel A, you can see two different clusters, and on channel B, you can see only one cluster. So I think I finished my presentation and a little bit over speak my time, sorry.
Okay, so in the next presentation, I will talk about some introduction to the RISC-V ISA. And so as we see in the previous presentation, in a complex system, there are parts which are computational intensive or latency sensitive, which should be implemented on some kind of special hardware. But there are some general tasks, for example, initializing the system, reading some parameters, setting some constant parameters, which are not time critical, but relatively complex. And in this case, some kind of microprocessor is a good choice. And I will talk about the RISC-V system, which is an open source implementation, and it is developed at University of California, Berkeley. And this is the 5th major ISA from that team. RISC-V is introduced in 1980, so it is 44 years ago. It's quite a long time. And the major design trade-offs are refined during these years and being incorporated into the new RISC-V architecture. So it is an open instruction set architecture, so you can download all the references and all the specifications for the instruction set from the internet, and you can implement your own RISC-V processor. And the system is designed to provide some base instruction, integer instruction set, but has some extensions, for example, floating point, atomic operations for multiprocessor operations, vector, and so on. Currently, it has two versions which accept 32 and 64-bit address spaces. So the question is, why to develop a new ISA? What is the problem with commercial ISA systems? So first of all, that they are proprietary. So if you buy the license, you don't get the right to redistribute it. So you don't able to create a system which has a fixed processor part and some configurable part by the user. And the different architectures are popular in different domains. For example, ARM processors are extensively used in the mobile space, and Intel x86 are used on desktop and server systems, and ARM and other vendors are used in embedded systems. So if you are working on one domain, then you are logged into some kind of processor vendor. On the other hand, processor vendors might disappear. So in the past, there were several microprocessor vendors such as Spark, MIPS, Alpha, Sun also created processors, but they are disappeared as either they are sold by larger companies or they went bankrupt. So in this case, even if you have the license for the ISA, you cannot work with it, and you cannot improve it. On the other hand, commercial ISAs are usually very complex. So, for example, let's take ARM, which started as a small RISC-type instruction set, but over the years, new and new features and instructions are added, and it is currently it is more a complex instruction set than a reduced instruction set processor. On the other hand, application binary interface is usually not included in the license, so it is possible that you will not able to run every application on your system which runs in the selected ISA. And in many cases, the designers of this ISA doesn't think about the extensibility of the instruction set. So it is not easy to add new instructions to the system because not used instruction code words are simply reserved by the creator of the ISA, and you cannot use it. And also, if you modify the ISA, the question is who will you get the compiler? So if you need to use a proprietary compiler, you need to buy either the license for that compiler to modify it, and this is not an easy task. So before going into details of the RISC-V design, first let's examine from some point the mainstream CISC processor, the Intel x86 architecture. So this architecture has 8 registers called AX, ABX, CX, DX, stack pointer, base pointer, special pointer, and data index. And these are so-called general purpose registers, but as the name suggests, the last 4 is related to some program organizing functions. The length of the instructions are varying, so it can be 1 byte to 50 byte. So when you fetch the instructions, you need to check the prefix and the opcode to find out whether another bytes contain additional fields to fully specify the actual instruction. So therefore, decoding and execution of these complex instructions is very complex and takes a long time. For example, if you would like to add just 2 numbers, we can do it 5 different ways. So it can be a register, so both the inputs and the result should be stored in a register. In this case, the instruction is 2 byte long. If we would like to use an immediate value to add to our registers, then the instruction becomes 3 byte instructions. If 2 operands are in registers and another source is from memory, then we need 6 bytes to define these instructions. Also, it is possible that the source and the destination is in memory. And in this case, if we use our registers, then there are 6 bytes. Otherwise, it takes 8 bytes. So the length of the instructions are different, and also the execution time. So it is very hard to create a control system for these complex instructions. To make things even more complex, the 2 memory addressing is in reality 5 type. So because we can use displacement, base addressing, base plus displacement, and some kind of scaling and other versions, each has different execution times, different lengths to make it more and more complicated. So in this case, we have lots of different instructions, lots of instruction type, and historically, these complex instructions help the assembly programmers in the 70s and 80s when compiler support or compilers wasn't advanced enough to do complex optimizations on the user code. And it's tried to narrow the so-called semantic gap, which means that the machine-level instructions and the high-level language instructions should be as close as possible. But it turns out that when these CISC architectures are used extensively, And some users started to measure the performance of the programs and measure how much instructions are executed from the large instruction set and how long time they are using the system. And it turns out that in some representative benchmarks, the measured instruction frequency and instruction histogram showed that the top most used instructions are executed 70% of the time. So the major part of the program is executed only 10 instructions. If we increase the number of instructions to 25, they are responsible for 90% of runtime. And in this case, we talk about roughly 300 instructions. So 10% of the instructions are used in 90% of the runtime. So it is a very skewed distribution because the most frequent instructions are usually function calls and data movement, which is 20 to 10% of time. And 25th quartile, so this is the 25th most frequent instruction, is executed only 1% on the runtime. So this is a very skewed distribution, and this means that in the instruction set, there are some instructions which used very frequently, and there are lots of other instructions which are used very rarely. And it turns out that and especially it is true for the x86 system too, that function call is slow because the parameters are usually passed using the stack between function calls. So the caller function places the input parameters to the stack, and the called function take these parameters from the stack and start processing. But usually this stack is located in the main memory. So the data movement, data flow looks like that data is written into the memory, and in the next step, it is immediately loaded by the called function to process data, and similar, the results are placed into the stack. Maybe it is written in the main memory, and when the function returns and we need the return value of the function, it is immediately loaded back. So it was clear that this point in the instruction set can be improved, and the improvement is rather simple. We need more registers, as many registers as we can use. And when designing the first RISC architecture, John Hennessy and David Patterson set up some design principles. First is simplicity favors regularity. So if we have simpler instructions where the length of the instructions, for example, are regular, then we can create more efficient systems. We can more easily load it, more easily decode it, and so on. The second is to make the common case fast. If we know that what are the instructions which are most commonly used in a processor, then let's try to make those instructions fast. And even if some special instructions are slower, we know that they are executed less frequently. So even if we replace them with a couple of instructions, we don't hurt the overall performance of the system. The third one is smaller is faster. This means that if you have less number of instructions, smaller code word for instructions, then it is faster to decode, and your system performance and the clock frequency can be higher. And the last one, that a good design demands good compromises. So the previous studies which examined the distribution of instructions during runtime showed that different type of programs use different parts of the instruction set. So a compiler, some scientific computation program, database management program use different part, so different 25 most frequent instruction from the system. But you can identify some instructions which is commonly used. And if you concentrate your design effort to these instructions and make the compromise that some instructions which are very handful for database management should be executed in 2 or 3 smaller instructions. It might be possible that even you need to execute more instructions, but because smaller is faster, your processor can run higher clock frequency, and as a result, you get better performance on the smaller processor, even if you need to execute more instructions. So let's try to think about how can we encode instructions and how large fields we need to encode instructions and the different fields. So let's assume that we need, to execute an instruction, we need the operation code. Let's assume that it is 8 bits. This means that 256 operations can be defined, as we see, because usually only 10 to 25 instructions are used by the programs. This is more than enough. Let's assume that we have operands. Usually, computation requires 1 or 2 operands. So, for example, we need to add 2 numbers or multiply them. Or maybe we need some fused multiple add. In this case, we need 3 operands, but generally 2 input operands is required. And they can be in memory. In this case, the instruction should follow 2 addresses for source 1 and source 2, and these addresses should be 32 or 64 bits, depending on the addressing space of the system. The alternative is to use registers, and in this case, the register index is required. And let's assume that we set it between 4 to 8 bits, and in this case, we can define 6 to 256 registers. In case of the destination, we also can use a memory or a registers. In case of a memory, we need another 32 or 64-bit field, while when using registers, an 8 to 4 bits field is enough for a very large number of registers. In many cases, it is very useful to use some constant value encoded into the instruction stream. For example, if we would like to increment a counter in case of a for loop, or we would like to access some field in a structure where we know the base of the structure and we should add the offset for the different fields, or we should increment a pointer to point to the next element of the array, and we know in advance in compile time what is the size of the elements in the array. So in this case, this immediate value is very useful, and because usually it is related to either a register or the memory. It should be as large as the machine word width of the system, so 32 or 64-bit field. If we add these elements together and assume that the instruction should access the main memory, in this case, we have an 8-bit field for the operation code and 4 64-bit fields for the 2 source operand, the destination, and the immediate value. And in this case, we get a very large 264-bit wide instruction vector, which is quite large. Otherwise, we can use some kind of load store architecture where each operation can be executed on registers, and only the load and store operation can access the memory. So in this case, we have an 8-bit operation code. Because we have 256 registers, we need 3 times 8 bits for the 2 source and the destination operation, and we need the immediate field, which is a 64-bit field. And in this case, we still have 96-bit wide instruction. But usually instructions using 2 source inputs a destination, and the immediate value are very rare. So in most cases, you don't need all of these fields. So this is when we need to do some compromise to reduce the instruction word size to a manageable size, for example, to 64 or even better to a 32-bit word. And this is which the RISC-V designers do. Before going into the details, let's overview the ISA. So in this case, the standard defined the base integer ISA, which must be present in all compatible system. It shows a minimal set of instructions which can be used to run a simple operating system and execute simple functions. It has two variants, the RV32i and RV64i, where 32 and 64-bit user-level address space is available. From the ground up and the beginning of the design, the system supported customization and specializations. So we have so-called standard extension. So I is the base and integer ISA, which can be extended by the M extension, which provides integer multiplication and division operations. E is for atomic instructions, which cannot be interrupted, and F and D, which is single and double precision instructions. And since then, for example, a vector extension is forming, and other standard extensions on the way. But the system can be extended, so-called non-standard instructions, which can be domain-specific. For example, AI and tensor operations can be implemented, or instructions which makes the energy efficiency of the system better, or some specialized instructions for processing network data or similar things. So the base instruction set provides 32 general purpose registers, which is really 31 because the register 0 is hardwired to constant 0, but actually the other 31 registers can be used freely. And we have only one user visible registers called PC. This is the program counter. And this integer ISA define only 40 unique instructions. And let's see in the next slide, the format of these instructions. So as you can see, there are 6 types of instructions, the R, I, S, B, U, and G type. And each instruction starts with a 7-bit field called opcode. This is the major opcode. And there is a restriction that bit 1 and 0 is fixed to 1, 1 in this 32-bit ISA, and is reserved for example, compressed instructions and other things. Yes, and the additional fields are the function 3 and function 7, which define that in the major opcode, what type of instructions should be executed. So for example, if we would like to do some arithmetic operations, then there is one operation code for the arithmetic functions, and the func 3 and func 7 fields will determine whether an addition, subtraction, logic operation, or other thing should be executed. There are 3 other important fields called RD and RS1. And RS2. So these are the source. RS1 and RS2 are the source register indices because we have 32 registers. They are 5-bit fields, and the RD is the destination register. And you should recognize that these fields are always in the same bit positions, so independent of the type of the instructions. And in some instruction types, some fields are not used. For example, the I-type instructions are used for immediate fields. So in this case, we don't need the second source register because we know that it will be a constant value. So we can use the func7 field and the rs2 field to form an intermediate value, in this case, 12-bit y. There are, in the other instruction, SB, U, and G type, also some kind of intermediate value is included. And if you see this, this encoding and the position of these fields, you feel confused why it is so complicated. But the design intent was in this case that if some field, bit field is used for some bits of the immediate value, let's try to reuse it in another instruction. So, for example, if we examine that that in the I type, these fields 11 to 5 in the and in the I type, and the S type is in the same position. So we don't, if we fetch the instruction from the memory, we can immediately place this field into the appropriate field of the immediate register. Similarly, in case of the U and G type, the immediate 19 to 12 and the U type 19 to 12 immediate are in the same bit positions. So you don't need a selector in this case. The most complex part of the system is the 11th IMM bit, which is in 3 positions in this case. So 1 position, 2 position, and 3 different positions. But in this case, we still need a 3-to-1 multiplexer because I don't find my pointer. But so you can see that here is the 4th position, and the 2 of them are a common position. So in this case, a 3-to-1 multiplexer is required. And in the other immediate field bits, only a 2-to-1 multiplexer is required. So this is to simplify the design of the processor. Of course, if your task is to create the assembly program, assembly compiler for the system, you will scratch your head to exactly position the bits. But in the final implementation, when the code is running, it will make things simpler and faster. Okay, let's examine the opcode field, because this is which provides you some customization. So there are instruction groups which are defined by bits instruction 4, 3, and 2, and 6 and 5. And you can see in this table that there are a major opcode for simple operation, this one, operation with immediate values. There are 2 major opcodes for the load and the store instruction, the branch instructions, the jump and link instructions, operation with immediate. In a 64-bit case, there are operation with 32-bit immediate and operation with 32-bit values. And you can see that there are some bit combinations which are reserved. And there are 4 custom bits, custom 0, 1, and custom 3, 2, and 3, which in the future may be used by the RV128 instruction set. But this means that basically you have 4 bits, 4 major instruction bits, which can be used for non-standard extensions, such a way that your system will be able to run any type of RISC-V code. So anyone with any compiler compile a RISC-V compatible binary, your system will be able to run it. And your special compiler, of course, can utilize these bits. So how many instructions can be encoded into this space? So actually, because the instruction bit is a 7-bit wide field, this means that we have 25 additional bits for to encode instructions. So 2 to the 25 different instructions can be used. If we prefer the standard layout to have 2 source and 1 destination register, in this case, we can use, we need 15 bits for encoding the register indices. And in this case, we have 10-bit remaining to define the different instructions. So this means that 2 to the 10, 1024 instructions can be added for each custom bit. So there are a large space to extend this instruction set with your special instructions. Okay, just briefly, I would like to show what are the main instructions. So there are so-called integer register operations. So you can see that the major opcode is the same for all. And the next 2 fields, the function 3 and the function 7 fields will determine whether addition, subtraction, the different logic and shifting and branch or conditional comparison operations should be executed. The next group is the load and store instructions. So in this case, because we have 1 source register and 1 destination registers, in the load case, we have a field for an immediate value. In this case, the immediate can be 12-bit wide signed immediate value, which means that from the source 1 registers, we can address plus minus 4 kilobyte address range, which in most programs more than enough. Similarly, in case of storing data, we can use this immediate field as a displacement automatically. This type of instructions, so the immediate field is very useful in accessing next element of the array or some fields in a structure. The other large group is the register immediate instructions. So in this case, the second operand is a constant, and it is encoded to 12-bit signed integer value. And this is also some recognition that most of the programs usually use small constant values. And if we need a larger constant value, we can use the load upper immediate instruction. So in this case, the upper bits from 31 to 12 can be set. And in the next step, we can use a simple add instruction to set the lower bits of the instruction. And also, when we are talking about some branch instructions, we can use the EIU EC, so which add the upper immediate to the PC value. And in this case, we can jump to any 32-bit location relative to the program counter. So similarly, in case of control transfer instructions, we use a 12-bit immediate because from the standard, the instruction should be placed on offset divisible by 2. Therefore, bit 0 can be 0. So we have a plus minus 4 kilobyte range for branching. And analyzing lots of source codes, it turns out that in a majority of the cases, the branches are usually referred to this area. And otherwise, we can use 2 instructions to jump to any location in the 32-bit addressing space. Okay. Another important instruction format is the jump and link, which can be used for function calls and return from function calls. In this case, we have a 20-bit offset, and which is also should be aligned to 2-byte boundary. So the 0 bit is 0, and in this case, there is a plus minus 1 megabyte range where we can jump relative to the PC. And in most programs, it is more than enough. If not, then we can use 2 instructions to jump to any position. Although the registers of the RISC-V system can be used arbitrarily, there are some rules which makes it easier for programs and for functions to exchange arguments. And in this case, we divide the registers to different groups. For example, temporary registers, coalesced registers, argument registers, and so on. And this means that, for example, using temporary registers, we don't need to save them because the caller function will not expect to find any useful value there. And also, when we call a function, we have S0, S1, and S2, S11 registers, which are the coalesced registers, where we can place, for example, a result, and A0, A7 is the argument register. So in this case, 8 arguments can be passed to a function. So it provides a very flexible way to exchange data. And in this case, the advantage is that you don't need to use the stack. So you can pass this data via the registers. And of course, if you need more data to send to a function, then you need additional space in the stack. So all in all, the RISC-V architecture provides a very flexible way to create a processor system, and its simplicity makes it possible to very easily create a working RISC-V processor, which can be later refined according to the requirements of the given algorithm, and it can be extended with special instructions, but the resulting architecture will be compatible with all the tools, compilers, and libraries which are already written for the RISC-V architecture. So, for example, you can easily run Linux on your custom generated RISC-V processor. So, thank you very much. And I would like to ask whether there are some questions. So if not, then I jump to my other presentation, which is a joint work with my former MSc student, Csaba Leitner. And in this case, we examined how can we store efficiently data for stencil-based computations. So what is stencil-based computation? Let's assume that we have an array, a 2 or 3D array, and we have some kind of pattern relative to some grid point. And according to this pattern, we should access data on the neighboring grid points, and we should compute some kind of function on these points. Usually, this kind of points are the result of some numerical solution of partial differential equations or image processing applications. On the right side, you can see in the simplest form when the yellow rectangle is surrounded by 8 neighbors, and this is the so-called nearest neighborhood template or kernel. So in this case, 9 values are used. In case of 3 dimension, the simplest organization is a 3 by 3 by 3 kernel. So in this case, 27 values can be used in the computation. And this kernel should be applied for each element of the array. Usually, we apply this kernel in a serial fashion. So we go through all the cells in a row-wise order. And let's compute how large memory bandwidth is required for this computation. If we assume a simple 100 megahertz clock, which is a not so high frequency on an FPGA, then taking into account the simplest nearest neighborhood template, we need to read 9 values and write the result. So it is 10 values altogether. If we use 32-bit floating point numbers, it requires 4 gigabyte per second bandwidth. In scientific computation, the 5-point stencil is used. In this case, only the left, right, top, and bottom, and the center cells are required. So in this case, only 5 reads are required and 1 write. In this case, the required bandwidth is smaller. It is 2.4 gigabyte per second. In 3 dimension, in the 3 by 3 by 3 case, we have 28 memory reads, 1 write, altogether 11 gigabyte per second. If only the sides, so left, right, top, bottom, up, and down cells are used, in this case, only 7 values should be read. And the result will be 3.2 gigabyte per second. So this is to load one array of floating point values. So in most cases, unfortunately, we have lots of data for each grid point. So for example, in a fluid dynamics simulation, we have 3 components for the fluid flow. We have the temperature, the pressure, some other parameters which model the complexity of the turbulence inside the cell. So in some cases, it is not rare that we have even 50 or 100 parameters for each grid cell. And in this case, of course, the bandwidth is 50 or 100 times higher, which cannot be provided by conventional memory system. But because we are executing these kernel computations in a serial way, it is possible that to locally store some part of the data, because the 2 neighboring computations are overlapped. So we don't need to reload lots of data. We can use the previously loaded ones. So in 2 dimension, you can see that roughly 2 lines and 2 additional grid points should be stored on the FPGA, because all the grid points on the top left corner of the figure will never used again, and the bottom right should be used in the future, but this single value should be loaded. So in this case, only 1 read and 1 write is required. The same thing can be done in 3 dimensions. I try to sketch how does it look like. Basically, this means that we need to store 2 plates, 2 lines, and some additional pixels. So in this case, we need larger memory, of course, and the 3rd dimension, and also in the 2-dimensional case, the 2nd dimension is free. So the length, the number of lines in the 2D image, and the number of plates in the 3D case is not determined. Only the width and the depth, and in the 2D, on the width of the grid. So so in this case, these values should be stored on the FPGA. So let's examine what type of memory resources we have on the FPGA. So we have the so-called block RAMs, which are 4 kilobyte memories. And in some FPGAs, we have URAMs, which are 32-bit kilobyte memories. So we can store 1,000 or 8,000 single precision floating point values in these RAMs. So you can see that because the memory buffer size is proportional to the width in a 2D case, relatively large arrays, so even an 8,000 element array can be easily handled on the FPGA. But in the 3-dimensional case, because complete plates should be stored, the size of the memory is quadratically depend on the dimension of the array. So on the right side, you can see that if we double the array size from 32 to 1024, the number of block RAMs required to store the two-plate storage increasing and hold the URAM values, you can clearly see that it is a quadratic relation, which is not the best. So if you would like to work on large 3D arrays, which required for accurate modeling of some physical phenomena, then we need partitioning. And the size of the partitions should be around 64 by 64 or 128 by 128. So this is the base of some columns, and the lengths can be arbitrary. So in this case, 8 block RAMs are required in case of 64 by 64 or 1 URAMs, and in the 128 case, 32 block RAMs or 1 URAM is required. The number of these RAMs depend on the type of the FPGA, but this is an order of 100 to 1 or 2,000. So in this case, we have enough space to store lots of time-dependent variables for a simulation. So 64 and 128 seems to be a sweet spot for an FPGA. So, okay, we have partitions, and this means that all data will be accessed after partition. So because for each computation of each grid cell, we need the neighbors. There will be 3 regions. So there will be a center region. So in this region of the partition, the data is exclusively read and write by the current partition. So no one else wants this data. It is surrounded by the inner hollow, and the thickness of this inner hollow depends on the neighborhood level. In case of the nearest neighborhood, this halo is 1 grid cell wide, but you can see in the right side that if the kernel is a 5 by 5 kernel, then it is 2 pixels wide. In this inner hollow region, this is allocated to the current partition, but these values should be read by the neighboring partitions too during computation of the edge grid points. And the yellow area is the outer hollow, which is assigned to another partition, but to compute the results of the inner hollow cells, we need to communicate values from the outer halo. So this means that if we layout our data in a common fashion, which means that we use, for example, row major ordering, then there can be blocks of the memory which one part is in the inner hollow, another part is an outer hollow. And to load them from the memory efficiently, we should examine how the DDR memory chips are look like. So the inner structure of the DDR memory chips is important. So I selected a 4 gigabit memory capacity chip, which in this case has a 4-bit wide bus. This is commonly used chip in DIMM modules. In this memory, the memory cells are organized in so-called banks. We have 16 banks organized into 6 bank groups, and each bank has an inner data bus width of 32 bits. So 32 bits of data can be moved between the bank and the temporary register. In the banks, we have 128,000 rows and 256 32-bit wide columns. And because the output data bus width is 4-bit and the inner bus width is 32-bit, when we need to read data, the inner bus data is 32-bit, and this is transferred to the outside world in 4-bit nibbles in 8 clock cycles. So therefore, an 8-element burst will be created. So this is the minimum size of data which we can read or write to this memory. How this memory is operated? So the first step is to provide the row and the bank address. So in this case, one complete row from the given bank will be opened and copied to a temporary register array. It is important that opening from a different bank or the same bank requires some time. So the activate commands cannot follow each other in some cases. So there is a restriction here. And also we need to wait for until the temporary registers are filled with the raw data. And this is called row address to column address delay. And in this type of memory, it is, in this case, is 17 clock cycles. In the next step, we need to select the column from the open row. So it is very important that if the row is open, we can access it. And to access another row, we must open it. And also, this reading has some latency, and this called the CAS latency, or CL. This is also, in this case, 17 clock cycles. After that, we can read and write the data. So we can move 32-bit data in and out to the memory chip. And finally, if this row is not required in the next step, we must close it. So in this case, the contents of the row, even if they are not modified, is written back into the memory cells, which is also requires 17 clock cycles. And after that, we can open a new row from the same bank. So it is a lengthy process. So considering a DDR4 memory module, which has a 64-bit data bus, we must read 8-bit long burst, which means that 64 bytes of data should be moved between the memory and the FPGA, and this is equal to 16 floating point values. And the time to open a row and access one memory element is 38 clock cycles, which is followed by the 8-element burst. Because this is the DDR memory, this requires 4 clock cycles. So in the worst case, the efficiency of the memory is only 9.5%. So if we need to read all the opening and closing times, we can achieve only that. Of course, because we have several banks, we don't need to wait the data from the first bank. We can open another bank from another bank group in the successive clock cycles. And in this case, if we lay out our data in a clever way, then using bank interleaving, we can achieve the theoretical peak performance. On the other hand, if we increase the size of data which we would like to read from the memory, for example, to read a complete row, it takes 128 bursts and results in 8 kilobytes of data movement. This is 2048 floating point values. And in this case, the efficiency will be around 90%. So the lesson to learn from here, to maximize the bandwidth from a DDR4 memory, you need to align arrays to at least a 64-byte boundary, but in the best case, a 8 kilobyte boundary, and read and write data in as long burst as possible. So this will pop up the question, how to align the partitions. So in this case, let's assume that we align the partition to the edge of the blue region. So each row in the inner hollow starting in a 64-byte boundary. So in this case, when we need data from the inner hollow, they can be accessed in a very efficient way. But we need data from the yellow region too, from here and there. And there is a cutout here to see. Sorry, the colors are not the best, but there is a lighter and darker yellow on the left and the right side, and you can see that this is the overlap, and this is one burst, and that is another burst. So this means that in this case, if we would like to access, for example, the left side of the inner hollow region, then the read will contain 16 floating point numbers, but only one element will be used. On the right side, similarly, only one element will be used, but we must read 16 elements. If we try to place the boundary to the edge of this yellow cell, for example here, then reading the first burst will be good, but when the other partition need this data, then it will see that only a partial burst can be executed. And let's examine how this degrade the performance. And you can see it in the bottom right side that as we set the width of the partition and from 16 to 4,000, what is the effect of the unused bursts? So in case of the 16 length partition, this means that for the inner hollow region, you need to read 16 elements. And from the left and the right, you only need one element, but you must read 64. So this means that you read 3 times 64 elements. This is 48 data elements, but you use only 80 of them. 60 from the center and 2 from the left and the right side. So in this case, the utilization of the memory bus will be lower than 40%. So even in an ideal case when you can fully utilize your memory, you can reach only less than 40% of the memory bandwidth. As the size of the hollow, the area of the blue part is increased, of course, there are more bursts in the inner hollow area, but less bursts in the outer hollow. So in this case, things getting better and better. And you can see that if we have 1024 sized partition, we nearly reach the theoretical peak performance of the system. The problem is that in a 3D implementation, we simply don't have enough local memory on the FPGA to store such a large partition. So some different way is required to store this data. And our solution is to subdivide the partitions according to the access time. So it is easier to show in 2D, but the same concept is working in 3D too. So we divide the partitions into the 4 corners, the 4 sides, top, the bottom, left, and right sides. And the size of these areas is depending on the size of the kernel. In the nearest neighbor kernel, these are 1 grid point. In larger kernels, they are a little bit thicker, and the central area, which is used by only this partition. And the trick is that we store each partition, sub-partition, in a row major order. So as you can see in the bottom right, so this is the corner cell. If it has more than 1 element, then it is stored in a row-wise order separately. And the bottom and top lines are also sorted. And very important that the green left and right sides are also stored in a row-wise order. So in this case, if we need to load from these memories, except the corners, they can be aligned to at least to the 64-byte boundary. And we hope that we don't waste lots of memory because of this alignment. So when we start reading, we can read it a complete burst immediately. And overall, we can improve the memory bandwidth utilization of the system. So what the system is operating. So for each partition, we have a 5x5 array of cells from the neighboring cells. So altogether, in this case, we have 25 areas. In 3D, we have 5 times more. So in this case, we have 125 regions. And we start at the top right corner. So first, we need to load all the corners. So in this case, the corners, not only corner C3 here, but the corresponding C0, C1, and C2 corners are also loaded and possibly reused during the computation, or if we have some special arrangement, then they are already loaded. So after that, we start loading the L2 and the own L0 parts, so these two parts started to load. And when this data is arrived, we can start placing this data into the input data stream of our architecture, namely the raw buffer. So in this case, first we put the top left C3 and the top C2, followed by the one line from the top L2 stream. This is followed by the top C3 and the top right C2. And after that, when we go one line down, we process or we should load the left C1 and our own C corner 0 element after our own L0 and the next two corners on the right. In the following, the left and right green areas and the own L1 area is loaded and put into the stream. So in this case, these side areas are prefetched. So we load one burst from each area. And in the center, we load one line. And in this case, we can place one element from S1, one element from S0, one line from L1, one element from S1, and one element from S0 again to the stream. And it should be repeated as many lines the L1 area has. And finally, we should process the last 10 docks in a similar way as we do in the beginning of the computation. So in this case, we load these values either from a local memory in the case of the corner or from directly from the DDR memory. So it is a rather complex memory access pattern. So we was curious whether it is working or not. So we created a test circuit, and this test circuit is only capable of executing the memory access patterns according to this subdivided data arrangement. And the reference was a system where only one partition is used in a row major order, and the size of this grid was 4096. So a very large array. So in this case, we think that we can achieve the maximum memory bandwidth. In this case, we used a two-dimensional arrangement. And we measured the memory bus utilization. And in this figure, the reference is the unpartitioned case when we have a two-dimensional 4000 by 4000 grid. And this is shown by the blue bars. And our proposed system bandwidth, relative bandwidth, is shown by the red bars. And you can see that we set the size of the partitions from 16 to 16 to 490 4100. And in each power of 2, around each power of 2, we have 2 measurements. And this corresponds to whether the alignment is to the center region, to the inner region, or the outer region. And you can see that as we expected from our model, the bandwidth utilization for 16, 32, and 64 sizes is rather small. So in the reference implementation, it is less than 40% or even 50%, while our special memory organization significantly improve the available memory bandwidth. So in this case, nearly 2 times higher bandwidth can be achieved. So even if we have a more complex data structure, we need to read from more locations from the memory, we still can improve the achievable memory bandwidth. It is important because usually these kernel-based stencil computations are memory bandwidth limited, so improving memory bandwidth makes our computation much faster. So what are the advantages of the proposed solution? So this means that the subpartitions can be stored in separate arrays. So there can be a separate array for the corner, separate array for the sides, separate corner for the array for the center element. Because the relationships between the neighboring cells can be defined by a structure which contains 25 or 125 pointers. Non-rectangular block structures computational domains can be defined. So if there are an area in the computation domain which is filled with some kind of body, and we don't want to waste no operation computations for this part, then we can omit this part. This also makes synchronization between partitions easier, because if we compute one partition and we would like to compute the neighboring partition, then we need data from the previous time step, not the updated. So in this case, the common solution is usually double buffering. So the entire data set is doubled, which doubles the data memory requirements, which means that the size of the array which we can simulate will be smaller. So in this case, we can utilize the fact that the central arrays will be never read by the neighbors. So the central areas shouldn't be duplicated. Only the corners, the size, and the plates in a 3-dimensional case should be doubled, which results in significant memory savings. On the other hand, when we would like to break this algorithm into multiple FPGAs, then the corner, side, and plate areas are which should be exchanged by the FPGAs. So we created a model to estimate the memory bandwidth in stencil computations. In case of partitioning, we find that there can be problems with memory bandwidth, and we proposed a new data layout for this, and created a test circuit to simulate the memory access pattern. And we find that in a 64 by 64 size partitions, 90% of the memory bandwidth utilization can be achieved, which is 10 times higher than the raw major storage case. In the future, we would like to extend the system to add some computational blocks and not just moving memory, but also do some useful work. And of course, we would like to test the system on FPGAs with more DDR4 channels and HBM channels. And in the future, it might be possible that DDR5 memories also should be checked. And the problem with DDR5 that the burst size is doubled again. So in this case, the wasted data of the transfer will be even higher. So thank you for your attention. And I ask whether anybody has a question. Okay, so our next speaker will be Levente Sántha. And Levente, the floor is yours. I'll just open your Singapore.
Okay, thank you. And I guess I am the last one. Thank you. Okay, so we are a little bit behind the schedule, so I try to be as fast as possible, and probably everybody is hungry. So, hello, my name is Levente Márk Sántha, and today I would like to speak about the fast multiple method and the implementation possibilities on different architecture of this method. The agenda of my speak, first of all, I would like to show the motivations of this method. Why should we work this? What is the problem behind this? After that, I would like to say some words about this fast multiple method in general, and then I trying to describe our first D and then our second D. So D means dimension, problems and the implementations of these works. So let's start with a very basic problem. Okay, I think after the high school graduation, everybody should solve this problem, basically. We have a one-dimensional space, so basically a line, okay? And we have particles, or in this case, charges, electrical charges on this line. As you can see, the space is normalized, so it's between 0 and 1, and we have 8 equidistant sections, okay? The question is the problem is, we would like to calculate the field, the electrostatic field at point X. It's a linear problem, so we can say that we calculate the effects of every charges and then sum up these parts, and this will be the result. So basically, it's a superposition, okay? It means if we have n charges, we have to take n multiple and accumulate. But what if we want to calculate the field at another point? We have to repeat this, okay? And if we want to calculate another point, we have to repeat this, and so on and so on. So if we want to describe the electrostatic field in this space, in this whole space, we have to do a lot of multiple and accumulation. Okay, because in every step we have to calculate, we have to sum up the effects of every charges. Okay, and this is the basic program. Determining this scalar potential, it doesn't matter that it's an electrostatic field or a magnetic field or it's a gravitation field. It's a really computation-intensive problem, and one of the greatest problem of the computation physics nowadays. And fast multiple method is a solution, let's say a solution for this problem. As you can see, the complexity is much more than this naive brute force method that I introduced on the previous slide. And as I have mentioned, or you can see, every kind of potential may be used by this method. So it really doesn't matter what kind of scalar field, scalar potential what we want to calculate. The first drawback of this method that it's really hard to implement. It has a complex mathematical background. And our question was at the beginning that is it worth to implement, especially on FPGAs? Okay, so what is this fast multiple method? What is the idea behind that? The problem is still the same. We want to calculate the scalar potential at point X. Okay, how should we do that? First of all, at the beginning of our calculations, we hasn't changed anything. So the closed charges is calculated as it was during the brute force solution. We sum up the direct field, the direct effect of them. But as we going further and further from our calculation point, we can say that the effects of these charges in the sections, it has not really changing in the section where X is laying. Therefore, we say that what if we just simply sum up the charges and inside in these sections and create a thing it's called multipole. So basically, we want to substitute this, in this case, for example, this the two charges in section -2 with 1. We also want to substitute the 5 charges in section -3 with 1 charges, and so on and so on. So we simply want to calculate the thing. This thing is called a multipole that has more or less the same effect as the charges in the sections. Okay. And if we do this, we can simplify our calculations, as you can see at the bottom of this slide. The green effect denoted by S, these are the direct effect. So it has nothing changed, just as we did during the brute force solution, take the direct effect. But the effects of the section 2, 3, and -2, -3, -4 is calculated by this simple thing. It's called multipole. And the result is, in this case, we have only 1, 2, 3, 4, 5, 6, 7. Okay, 7 calculation and 7 sums. So basically 7 multipole and accumulate, more or less. The other interesting thing of this method that we can generate a multipole from multipoles, not just from the basic particles. So we can make a tree-like hierarchy. And if the original charges are far, oh, sorry, I didn't want to. So if the original charges are far enough, we can we can calculate the effects of them with a higher order multipole. If I want to show the previous example with the tree representation that I have mentioned, we can say that in the sections denoted by green, that's the direct calculation. So just like the brute force solution, but the nodes denoted by purple, well, the colors may be not the best, are calculated with this multiple substitution. And as you can see at the left, we used a higher order multiple that was generated from 2 multiple because the charges are far, let's say, far enough to do that. Of course, as you may have some impression, this is an estimation. So it's gonna have some error, okay? But I don't want to go the mathematical details, but this error can be kept above a desired level. The error level determines the order of the multiple, so how much, let's say, number can represent a multiple. If we want to keep the error lower, we need a higher order polynomial to represent a multipole. But this can be determined, and it has the mathematical background, and it's proven that this can be done in every cases. Okay, so in our first investigation, we did this one-dimensional implementation. We used around 60,000 particles, and during our research, we said, let's on a PC, we said, let's turn on hyperthreading and turbo. Yeah, so it can be criticized that why we turned on these things, because it can be cause a thermal throttling, which is a non-deterministic effects of PFIS. So the results are not can be regenerated at the same. But this is the everyday use case. When a scientist goes to his computer, these things will be turned on. So to make a much more real life case, we said, let's keep these things turned on and do more runs, do more evaluations, and take the average. This representation is much more closer to a real life effect and a real life function of the original program. The error level was chosen to 10 to minus 2. You can see which operating system, compiler, and 6 things like that were used during our research. We used the floating point representation in the multiples and the charges and their position too. And a little twist, we changed the kernel size. This is basically a gravitation kernel. But as I've mentioned, from the point of the fast multiple method, the kernel doesn't, the original kernel, the original scalar fit doesn't really matter because the generation of this hierarchy of this T does not really change. And when I am speaking about the FPGA implementation, it's always a ZCU 102 FPGA evolution kit, and this runs at 100 megahertz. Okay. So we have different configurations, and we did a lot of measurements, as I have mentioned. We used a lot of parallel threads. And we also measured the speed of the brute force calculation to compare whether the FMM is worse or not. Okay, the best case in the brute force scenario was around 4 microseconds assumption. Yeah, it's 4 microseconds. So let's jump to the FMM solution, also still on PC. As you can still have several configurations, several runs. But now you can see 2 charts. One is the evaluation of the average evaluation time of the field, and the other one is the tree generation. Because when we want to use the fast multi-method, the first step is always to generate the tree here that I have shown you previously. This is always the first step. It takes some time. Okay, but after we build this tree hierarchy, the computation can be much more higher. Okay, it also means that it's only worse when we have a pretty big, let's say a pretty big field. If we have just a really small one, it simply doesn't work to build the tree and use this kind of calculation. Okay. Also, to make a fair implementation, we implemented the brute force method on an FPGA. Let's say how fast it can be. It's a highly parallel version of the brute force method, because we also divided the evaluation points, so multiple evaluation points calculated in parallel, and the calculation of one evaluation point is also parallelized in this figure. We calculate 4 evaluation points, as you can see, P1, P2, P3, and P4, and the calculation of this evaluation points also paralleled by 2, because we have attached 2 arithmetic logic by every evaluation point. It's just for my presentation in the, let's say, real life version. 32 position is calculated, 32 evaluation point is calculated in parallel. But one evaluation point is parallelized by 2, as you can see in this figure. So it's the same. After that, we made a simple, let's say, naive FMM solver, also an FPGA. Nothing really special. We built the tree, calculate the multiple coefficients, and we made an evaluation model and store the results. So basically, nothing special, no parallelism in this design in general. Just let me show the best results we have achieved during this work, during this process. So when we speaking about a PC and just one thread, so no parallelism method, the evaluation of 1 point was around 20 microseconds when we used the brute force method, and it was 1.5, let's say 1.5 microseconds when we speak about the fast multiple method. But on the other hand, as you can see, setting up the tree, it takes 45 milliseconds, milliseconds. So it takes some time, but if you compare the evaluation times, if we have several evaluation points, it's simply worth to build up this tree. The results, it's more or like the same when we use the multi-thread version of the brute force method and the FMM method on PC. And as you can see, it's more or less the same when we speak about the FPGA. Of course, or you can see that there is no an FMM parallel version of this one dissolver because at this point we saw that comparing the brute force results and the naive results of the PCs. So basically on an FPGA, it was more, that's 2 times more than the one thread solution, but it's the same league. So the change is not 2 times, not 10 times or 100 times and so on. And the power consumption was much more or less when we speak about the FPGA. It's the TDP is around 5 watts, comparing with a PC, which can be around 100 watts. So we decided to move to 2-dimensional problems because we saw that it's worth to investigate that's a more real-life problem, not just a very theoretical 1-dimensional problem. So what has changed, what is changing when we speak about 2-dimensional problems instead of 1-dimensional problems? First of all, we don't have segments. We have, let's say, squares. So we have areas, and every charge is in this area, in this square, should be make the multiple. And of course, as you can see, now 4 multiples can make another multiple, not just 2. That means we have to change our tree hierarchy. So every multiple every higher order multiple is generated from 4 original multiple. Okay, and yeah, that's what has basically changed, and it has some other drawbacks. Of course, it's too small, I guess. At least on my screen, it's too small. But I try to show here that if we want to calculate the field at X at a step, which particles, which multiples are used, and in the next steps, which particles and which multiples are used. As you can see, if we are at the border, at the separation border between the stages, it simply flips which original sources and which multiples are used. And in general, we can say that 6 lines of raw data should be kept. It doesn't matter we speak about the particles or we speak about the multiples. we can generally say that 6 lines of each level should be kept in memory to be able to calculate the field at point X as fast as possible. And another problem is that, okay, we know that thing, but how to store this data in the memory to be able to access as fast as possible? I think you have already seen something similar in the previous presentation, because our solution was a zero order representation, a zero order pattern. This was examined by a thing it's called neighboring matrices. In a neighborhood matrix, you can see that at an evaluation point, which memory cells, which particles should be in the direct cache, in the FPGA, or in the cache of a PC, to be able to calculate the problem as fast as possible. On the left-hand side, you can see more or less a traditional linear representation. On the right-hand side, you can see this zero order pattern when we store the data in this zero order pattern. And as the wide of this matrix is the bandwidth that is required. As you can see on the right-hand side, I guess it's 3 times less or something. The result was something like that, it was around 60 at the normal representation, and it's about 20 when we speak about this zero order neighboring. And at the right corner, you can see the zero order representation. So this matrix is the positions in the real life, and the numbers in the brackets, it represent the positions in the memory. So as you can see, the very beginning, the first element is, yes, is stored at the beginning of the memory, then the second, but after that, the next line, first element is stored in the memory, and so on, and so on, and so on, and so on. These were just some basic highlights of our problems, but maybe I have already run out of time, so I don't want to waste of yours too much. Our results, when we speak about these two, the representation and average evaluation runtime on the FPGA was about 1.1 microseconds. On a PC, it was around, let's say, 6 milliseconds. But to be fair, there are no optimization applied on the PC version, and this means a lot of cache miss appears, and this is the result why it is slow. If we have do some PC optimized version, this number can be reduced, but it still would be around 1 millisecond or even more. And of course, the TDP, so the power consumption, it's still much more lower when we speak about an FPGA than a traditional PC. Don't even mention a high performance PC or any kind of server. So at this point where we are now, we made successfully made some 1-dimensional and 2-dimensional FMM solver, but it's a work in progress. So what we want to achieve, make it bigger, make it faster, one day maybe even 3D problems, make more fair comparisons, and also it would be nice to measure these problems on a GPU. But that was my presentation. Really thanks for your time. I really appreciate it. If you have any questions, feel free to ask them. If not, enjoy your meal and thank you for your attention.
Okay, so thank you very much, Levente, for this interesting presentation. And this was the last presentation, and then we are over time. So I would like to thank all of your kind attention, and I hope that you gain some useful glimpse of information about designing some application-specific circuits and its advantages. So thank you very much, and have a nice day. Bye.